Let's take a look at descriptive statistics. Last week, we uh, we looked at descriptive statistics for numerical variables, age, weight, so on and so forth. We're going to take a look at that now. I'm going to click on Analyze, Descriptive Statistics, and I notice that after frequencies, my next selection is descriptives. Okay, I'm going to click on that. And just as we did before, we can see that we can choose, let's see, let's pick out a numerical variable, age of mother. We actually did that in Excel. We calculated the mean earlier on. I can indicate to SPSS which variable that I want to work with in calculating my descriptive statistics. I can, if I want, do more than one variable at the same time. To keep things simple, I'm just going to use one variable here. But you can move in as many numerical variables as you want to do this calculation. Options, SPSS is going to do a bunch of calculations. It's going to calculate the mean, telling me it's going to calculate standard deviation. I'll tell it calculate the variance too. Let's calculate the range also. Okay, and I'm going to say continue. I'm happy with that for now. And then I'm going to say okay. You didn't have to go into options. It was already going to do the mean and standard deviation. Very frequently, that's enough. But I turned on some other calculations as well. Okay, I'm going to click OK. SPSS very quickly returns a lot of interesting data for me. I'm going to repeat this because it's all the way down at the bottom, and sometimes I know that when you're broadcasting this kind of stuff, sometimes it's not easy to see what's at the bottom of the screen. So if I look at this, let's see, descriptive statistics. Okay, age of the mother in years. Okay, now we got 800 cases. The range is 27. The youngest woman is 15. The oldest is 42. The range is the difference 15 to 42, 27 years. The mean, 26.92. That should look a little familiar because that's what we got as well. I think that it rounded it a little bit, and it's probably rounded based on the number of decimal places that we defined when we coded it. Standard deviation is 6.107. The variance is 37.299. Based on what last week and when we did Excel and we calculated the variance manually and the standard deviation manually, can anybody tell me the relationship between the variance and the standard deviation? Come on, a volunteer. Give me a volunteer. What's the relationship between the variance and the standard? Variance is equal to the standard deviation squared. Exactly. The way we calculated the standard deviation is we took the variance, 37.299, and we found the square root of it, 6.107. Bingo, that's exactly what we got there. Okay, perfect. Exactly. Thank you very much, guys. I got a couple of good answers on that. A couple of you guys are shy. You like to send private messages. That's okay. I don't mind. The previous semesters, very few people sent private messages. That's why, and they're highlighted in red. So it kind of threw me off a little bit there. I hadn't seen it before, at least not very often. How is the variance useful? Well, the variance is used in some calculations. More frequently, the variance and the sum of squares, the precursor for the variance, before we divide it by n minus one, the sum of squares is used later on in the semester in a calculation called analysis of variance. The variance is used in some calculations as well, but the standard deviation is the one that we wind up using the most. But actually, the variance, is something that we're going to see has some value in future calculations. Right now, in the descriptive statistics that we're working with right now, and histograms and normal distributions, for the most part, for the next, I'd say, 4 or 5 weeks, we're going to be way more interested in standard deviation than the variance or the sum of squares. But it'll come up again. It'll raise its ugly head, as I like to say later on. Okay, and again, you can click on this table, copy it, and you can install it into a Word document or a report or something like that. So you guys already have a tool now that you can use in another class if you want to produce well-formatted charts, well-formatted tables with descriptive statistics and so on and so forth. So you have a tool right now you didn't have before. You can add this to your resume. The bottom of your resume from now on, everybody go home and say knowledge of SPSS. Okay, and we'll all get higher paying jobs, hopefully. Maybe not me. I'm too old for for another job. Okay, so at any rate, so now I want to show you another exercise, another way for us to do this, another way for us to do the same thing in Analyze. I'm going to click in Analyze. I'm going to go to Descriptive Statistics, and I'm going to go to the next selection, which is Explore. Okay, notice I have more options here. I don't have just that one box. I also have more buttons for options here as well. I'm going to use the same thing I just used, which is the age of the mother, numerical variable. I'm going to move it into dependence lists. SPSS usually defines the variable that you're calculating statistics for as the dependent variable. Okay, it's the dependence. I put it in the dependence list. I'm not going to worry about factor list for now. I'm going to click on statistics. Statistics, it says calculate. Now, it doesn't ask you for a lot of detail on what you want to calculate and what you don't, because it says if you click off descriptive statistics, I'm going to calculate everything. So you don't have to check off a lot of boxes. Everything you can think of as descriptive statistics. We have an opportunity to put in a number for something called the confidence interval. That's going to come up in about maybe 2-3 weeks or something like that. For right now, I'm going to leave that at 95%. And it's going to be more meaningful in a few weeks than it is right now. But I wouldn't worry about that right at this stage. So I'm going to click continue. Under plots, well, you can produce a stem and leaf plot, which it does which you can ask it to. You can ask it to produce a histogram. You can ask it to produce a whole bunch of other stuff. I'm going to turn those two off. I just want the data box for right now. Options, you got different ways of looking at the data. I'm not going to worry about that for right now. Right now, all I'm going to do is age of the mother and descriptive statistics. I'm going to click OK. Doesn't look like much, except look at the difference now. Instead of getting just the mean and standard deviation, now I get a confidence interval, I get the median, the variance, the standard deviation, the minimum, maximum, the range, the interquartile range. We're going to talk about that in a few minutes. Skewness, so on and so forth, a description of whether or not it's normally distributed. I get it automatically plotting me a box plot. Okay, I didn't ask for it, did it automatically. Age of the mother in years gives me a box plot. I'm going to go back to Analyze, Descriptive Statistics, Explore, except this time I'm going to go into plots. I can say, give me a stem and leaf plot, give me a histogram, give me the works. Okay, I can say, okay. Notice down here you also have to click both, but that's normally automatically displayed. Okay, so what do I get? I get my descriptive data, all sorts of descriptive statistics very quickly. And I get my histogram. Now, what is my histogram? My histogram is a continuous bar, kind of like a bar plot, vertical bar plot, but the variable is continuous. They touch each other. So in other words, where it says 30 here, it really represents 29.5 to 30.49999, right? There's always going to be a place for any age to fit into all of these. And what is our expectation if this is normally distributed? Normally distributed means most of the values are going to be in the middle. It's going to be bell-shaped, presumably symmetrical. And as we move on in the semester, this is going to be a very important shape for us because it makes the way the data is distributed predictable. We can start to make predictions about the real. Remember, this is a sample of 800 people out of a much larger population. It gives us a way to make judgments about the entire population based on the way that this histogram is distributed. So this is going to be important stuff to us. Stem and leaf plot. Stem and leaf plot is just another way to visually represent the data. It's kind of a little bit out of date because most people like histograms. If you look at it, it's really just a histogram on its side. So for instance, this represents the frequency of of women that were 15. There were 5 women that were 15, and that's represented by a value 1 and 5 fives. The fives represent, that winds up representing a column representing 5 women. How about how many women were 16 or 17? One, and each one of these sixes represents a woman that's 16 and 17. And this one represents one and number of women that were 18 or 19, and so on and so forth. So that winds up making a uh, 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 a uh, 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 a sideways histogram that kind of describes this shape as the same shape that we're looking up as well. This used to be much more popular as a way to display data when computers were a little bit more primitive and we needed to use, and all we could display was numbers and letters, and we wanted to display it graphically. This was useful because we couldn't display this picture, right? And believe it or not, there was a time when you had screens that did not display graphics; they just displayed characters, numbers, ASCII characters, numbers and letters, so that you would wind up displaying something like this. I don't know if you guys have ever seen it. I can show you pictures, but a lot of people in those days, in order to simulate pictures, images on computers that could only display numbers and letters, used to produce what's called ASCII art. ASCII is a American Society for Character, something or other. It's a standard for how to display numbers and letters on a screen. And they would actually produce, say, a picture of the Mona Lisa that's printed out in numbers and letters. You may have seen that years ago. If anybody's interested, they can drop me an email and I'll give you a couple of links and stuff like that. If you Google ASCII art, you'll see lots of these kinds of images. But it's because back in those days, that's all we could display on a screen. So stem and leaf plots had some use then. Probably won't use it much anymore. Okay, and it also produced a box plot. Can anybody tell me what this bottom, it's called a leaf, that little line there, and this line up here is called a leaf, what the bottom leaf represents? Right? Bottom leaf is down by 15. It represents the minimum, the lowest value. Exactly. Similarly, the top leaf represents the highest value. The oldest woman in this study that gave birth was about 42 or 3, right? Now, how about the bottom of this grayed out box, whatever color? I can't, I never can describe that color. Okay, the bottom of this box is a percentile. What percentile is it? Okay, the second quartile, or in other words, another way of saying second quartile is second quarter is the 25th percentile. In other words, 25% of the women were below, looks like about 22. And this is the third quartile, the top line here. And that represents, let's see, that look represents, I guess, about 33 years old or something like that. So the 75th percentile, 75% of the women were below 33, and 25% of the women were above 33. Excuse me, 33. So the range from the bottom of this box to the top of this box is the range from the second quartile to the third quartile. The 25th percentile to the 75th percentile represents 50% of the women. The middle 50%, or another word for it, is the interquartile range. You might have remembered that it actually calculated that for the interquartile range was 10 years for us. In other words, it went from 22 to 32. Okay, that's what that was. How about this black bar in the middle, this dark bar in the middle? Anyone want to take a wing at that? What's that black bar? Mean is an excellent guess. It's wrong, but it's an excellent guess. Okay. In fact, I would have assumed if I were doing this from scratch, I would have assumed that this would have mean as well. It's actually the median, the middle value. Kind of makes sense because this is zero percentile, nobody, right? This is the 25th percentile. This is the 50th percentile. Half the people are below, half the people are above. So it makes sense in a box plot that black bar would be the median rather than the mean. Okay, and 75th and 100th percentile. Okay, so now notice the median is not in the middle. And so you would usually expect the median and the average, the mean, to be the same, and this bar to be right in the middle. What does it tell you if this bar is not in the middle? That the range for women that are above this age is wider than the range of women that are below the middle value. What does that tell you? You don't have to feel bad about that. So don't worry about that. We're learning here. Wrong answers are better than right answers in some cases. It's skewed. In other words, it's not really a normal distribution. Let me see if I can't see it here. You can kind of catch that here if you look at the shape of this. Like, you look how sharp this goes up over here and comes down over here. You would expect that this would end over, that it would be something like this, right? But we have some extra values up here at the high end. So it's actually as if that this, if it were, it could have been a little bit more dramatic where we had values out here. So it would look something like that. So it's not that dramatic, but you can see that there's values here that tend to pull the mean to the right. So the median is no longer in the middle, it's below the middle or below the average. Okay, and we see that here, it's below the average. So this suggests that it's skewed positively towards the higher numbers, or in other words, to the higher numbers or to the right. When you look at it horizontally, it's skewed right. Okay, so that's one of the ways we can kind of spot that on a histogram. It's not really that dramatic, but you can kind of see. Okay, but it's even more easily spotted here because you can see that the values, the maximum values are further away from the median than the minimum values are. Right. So when we say skewed to the right, we mean the mean is pulled towards the right. Okay, so let's move on to the next part of this. And I want to show you something else here. Analyze descriptive statistics. I'm going to go back into Explore because Explore gives us another valuable tool that's really important to us. Click Explore. I'm going to stay this. His age of the mother is in here, right? Notice there's a box here called Factor. Factor is another way to say to split something up into parts, right? When you factor a quadratic equation, you factor it into two parts that are, when they multiply each other, give you the original formula. When you factor a number like 15, you factor it into 5 and 3 because 5 and 3 will give you 15, right? So this splits it up into parts. So what parts might we want to split up the age of the mother? Well, let's say we want to split it up. See, now it's going to have to be a categorical variable because we don't want to split it up into a million different pieces. We just want to split it up into, say, ethnic groups, or the race of the mother. Or how about, let me see, how about comparing the age of mothers that smoked during pregnancy versus the ones that didn't smoke during pregnancy? I'm going to move that in there. I'm going to click OK and see what it does. Well, take a look at this. It separates this into two groups. There were 684 mothers that didn't smoke during pregnancy, right? And their average age, and that's 114. The average age of mothers that didn't smoke during pregnancy was 27. The average age of mothers that did smoke during pregnancy was lower. Younger mothers tend to smoke during pregnancy than older mothers, right? I guess for a lot of reasons. I'm going to do this a little bit. I'm going to do a different one. So what did that do for us? It allowed us to split the data so that we can analyze two groups separately. I see there's a couple of questions, so I'm going to get to them in a second. Okay, notice it also gave us the box plots side by side. This box plot represents mothers who did not smoke during pregnancy. This represents mothers who did smoke during pregnancy. There's a lot of overlap, but we can kind of see that the median value for mothers who did smoke during pregnancy is quite a bit lower than the median value, the middle value, for mothers who did not smoke during pregnancy. Okay, so we can see some interesting stuff there. We can see there's less variability in this group than there is in this group. This one's spread out more, and so on and so forth. Because that could just be because it's a much bigger group. Okay, you could do it for gender, you could do it for race, you could do it for any number of other things. Let me do it for something that makes a little bit more sense. Descriptive statistics, Explore. Now, Explore is giving you descriptive statistics still. Except this time, I'm going to look at whether or not the mother smoked during pregnancy. Okay, excuse me. I'm going to look for the weight of the child in grams. I'm going to analyze the descriptors. That's a numerical variable. I can do descriptive statistics. And I'm going to break that up into two groups: mothers that smoked during pregnancy and mothers that didn't. That sounds interesting, doesn't it? I think you probably would guess at what we're looking for here. Because let's take a look at this. Here, you get two histograms: one histogram for mothers that smoked, one histogram for mothers that didn't smoke. Notice this is left skewed, and so this one's left skewed also. But let's take a look at these box plots side by side. Okay, and what we see is that we see that mothers that did not smoke during pregnancy and median weight of the baby that did not smoke during pregnancy is the left one. The median weight of the baby was greater than mothers who did smoke during pregnancy. Anybody know what these extra little dots and so on and so forth are here that are shown on this box plot? Want to hazard a guess? Those are outliers. Those are a situation which the SPSS has done a calculation. As we move on, we'll explain how it does that calculation. And what it's saying is that that particular value and that particular value, and it gives different values for stars and circles, those values are so far away from the bulk of the rest of the values that it's telling you that you might want to consider dropping them out because, thank you, Paulette. So I get it. I know I'm that way too sometimes. Is You distracted me now. The the outline suggesting that you might want to consider whether or not you want to eliminate that data because it's so far from the bulk of the data that you collected that there might be reason for you to re-examine those and see if there's some other factor beyond the ones that you're examining that would cause those numbers to be so different. I mean, the birth weight of these babies here, obviously very, very, very low. And this very, very, very low. So these are clearly premature babies. Maybe you don't want to include premature babies in this study. You just want to get an average idea of whether smoking in general reduces birth weight, but you don't want to include babies that might have been premature for a number of other reasons as well. So it gives you a reason, a way to examine it. This case, this one's really kind of messy. But you see how you can separate the data using Explore. So you go into analyze descriptive statistics. We've learned three functions now: frequencies, which we use for categorical or nominal data names; descriptives, which gives us our descriptive statistics; explore, which expands the amount of information that we get in our descriptive statistics, plus gives us the opportunity to separate groups out so we can compare them. If I had used ethnicity, we might have gotten six box plots right next to each other on the same graph. This represents the highest value in this group, the highest value in this group. This one represents, I think it's 1.5 times, 1.5 times the difference between the median and the 70, 1.5 times the standard deviation. I'd have to look it up, but SPSS has actually a way you can even adjust the way it judged what's an outlier, but it's based on the difference between that value and the highest values that are, I think, maybe 1.5 times the difference between the median and the next percent and the next quadrant quartile or something like that. I'd have to really look it up to tell you for sure. For the moment, just keep in mind that that's what they're suggesting to it. Let me go back over these questions. There's a number of them. 1.5 times the interquartile range. I'm thinking that might be it. Emily, I think, kind of guessed at that ahead of time, but it doesn't look like that, does it? Because that would be about there and there. It looks like it's a little bit wider. I'd have to really take a look at it. It's in the documentation, and I think you may also be able to alter how it calculates it. The whiskers again, minimum and maximum value, at least the ones that it's suggesting that you work with it. Smoking. Less women smoked than did not smoke. Anyway, I can't tell. Well, we can tell that women that smoked had lower weight babies than women that didn't smoke, right? This is the median value. Notice it's in pretty much in the middle, so maybe it's kind of like the average also. The median middle value of weights for the middle value for weights of children of women that didn't smoke is about 3,400 grams, and for women that did smoke, it's about 3,200 grams. So on the average, it looks like they were. Oh, okay. So yeah, somebody mentioned that in the lecture. It came up what rule that SPSS is using to determine what's a suggested outlier. I mean you have to consider an outlier. When it does a calculation, it does all the values. Not it doesn't unless you tell it to eliminate the outliers. Okay, so we're going to talk correlation is a special word. Let's not talk about correlation now because that's a whole nother kind of statistic. Okay, we're just talking about right now about comparing two groups based on samples and comparing their means, how much the values vary within them. Yeah, it comes to relationships in a sense. Correlation is a special thing that we're going to learn about as we move forward. So that's a special word to statisticians. It's used one way in language, but it's used in a special way when you're a statistician. Okay, so let's move on to something else. There's instructions on how to produce a dot plot, which is very similar to a stem and leaf plot. I'm not going to bother with that because it's almost identical. There are instructions uh, uh, in the exercise that shows you how to do that. I'm not going to bother with that here because it's almost identical to what you would get with stem and leaf. And you got the sequence of instructions on how to use the graphs. Go to Legacy Dialog, go to Scatter, go from there to Simple Dot or Simple Dot, and from there define it and tell it what variable that you want on the x-axis. And let's say we wanted the age of the mothers on the x-axis. We can add a title to it, so on and so forth. We can separate the variables different ways. We're not going to do that. I'm going to click OK, and you can see it produces each one of these dots represents women that are in the range of 20 years old, or either that or between 19.5 and 21 and 20.5 wind up in here, and so on and so forth. And it's almost exactly the same as your stem and leaf plot. Instead of using numbers, they just use little circles and stuff like that. Okay, so we're not going to worry about that too much. Stem and leaf. Stem and leaf, we saw we could produce one from our statistics. You can also go to graphs and legacy dialogues and go to for stem and leaf. Let's see, where am I going to go for stem and leaf? I'm going to go to no, I don't think you can get it from here. Stem and leaf scatter dot histogram. Maybe in histograms. Nope. Yeah, I guess it looks like stem and leaf. You got to go to descriptive statistics and check off stem and leaf either here. Oops. In Explore, analyze, descriptive statistics, Explore. You go in here, go into plots, and you can check off stem and leaf. Apparently it's not available in graphs. I'll have to look again. I'll look again tonight, but that's easy enough to do. And again, not something you use very often in real life anymore, in these days anyway. Let's see what else we got that's interesting here that we can play with. Box plots, we kind of saw that already. Let me see. Graphs, legacy dialogues, box plot. Okay. Let's look at a simple box plot. And let's see, simple box plot. Variable. Let's see, for a box plot, let's get something we haven't looked at yet that's numerical. Weight gain during pregnancy. Let's take a look at a box plot for that. We have some options. I'm just going to I'm going to just go ahead and go straight through. We'll play with the options as we get a little bit more sophisticated. Maybe, let's see, summaries, box plots, category axis. Variable is summaries is separate variables. Simple weight gain during pregnancy. Let's go for the category axes. Let's see if I can't get it to, maybe it wants to separate this into, say, sex of the child. Okay, say okay. Okay, and in fact, what it did there, if you notice what I did there, was I asked it, I go back here, graphs, maybe to preserve. A lot of times in these analysis, preserve what you did last time. Simple, define. I asked it to give me a box plot for the weight gain during pregnancy, and I asked it to break it up into two groups: sex of the child, male and female. Let's see if there's a difference in weight gain for males and female babies. And it did it for me. And boy, it doesn't look like there's much difference, right? A little bit more variability, a few outliers, but it looks like the amount of weight gained when the infant was a male is very similar to what it was for a female. Anybody know whether or not that's true? Is there a difference in weight gain by the gender of the child? I would have expected generally female infants are smaller than males, but I could be wrong. And you guys are, like many of you guys are nursing people. I'm an EOHS person, so historically, yeah. Female infants are heavier. No kidding. Right now, remember, this is just an example of something that we've done. Case study, side by side. Let me actually analyze the data. Explore, weighted child, weight gained. I want weight gained. Let's see, weight gained during pregnancy and gender of the child, sex of the child. See what the actual numbers are. Statistics. Yeah, we got them all. Say okay. See what these numbers look like. Notice how we as we're working with this, I'm asking myself questions about this data. And as I ask myself questions about this data, I can actually answer these questions by having SPSS calculator for me. Well, the mean weight in this study for male children that are born is, I guess, what is that? What did I wind up calculating here? Descriptors, weight gain. Weight gain during. Oh, I'm sorry. I was doing weight gain during pregnancy, not the weight of the baby. So there doesn't seem to be much of a difference. 30.69 pounds on average for male babies and 30.46 for female babies. So, in case somebody was trying to predict this and telling people, well, I think you're going to have a female baby because you're not gaining that much weight, looks like they'd be pretty wrong, right? Doesn't look like there's a significant difference. In fact, this 95% confidence interval tells us that we're 95% sure the true population mean for all babies in North Carolina is between these two numbers, and for females between these two numbers. We're going to learn how to use that to make predictions about whether or not we can say things are different with some confidence, whether or not there really is a difference between male and female babies with some extra confidence. So, but I wouldn't worry about that now. It's just, this is a good example of, we can start to use SPSS to really examine the data in a lot of different ways. And we're going to be taking advantage of that quite a bit as we move forward. Okay, so I think there's one other exercise that's in here, and let's see if we can't make this work. I want to do this. Oh, we got about 2 minutes left. So I'm going to do this quickly, and then we're going to call it a night. I'm going to go to, let's see, Analyze, Descriptive Statistics, Explore. Except this time, I'm looking at the weight gain during pregnancy. Okay, I'm going to get rid of the factor here. I'm going to go into statistics, and I'm going to check off percentiles, because that's going to give us a useful statistic that might be hard for us to calculate otherwise. Remember, this is the weight gain during pregnancy, right? No factor, just all of the women that gained weight that were in this study. How much weight did they gain during pregnancy? I'm going to click OK, and it's going to give me a box, an output box. Run it a little slower now. Come on. Let me try it again. Did it do it? Weight gain during pregnancy. Here we go. Percentiles. I had a lot of other statistics checked off there. That's why I got so much stuff there. Remember, I didn't go back in there and check everything off. It's telling me that the 25th percentile. Let's see. Weight gain during pregnancy in pounds. The 25th percentile is about 20 pounds. The 75th percentile is about 75 pounds. I suspect that, let's see, weighted average, weight gain during pregnancy. It's predicting our 25th percentile is around 20, 75th percentile is around 40. I'm not so sure that we got into something that's a little bit more complicated than I intended here in terms of how it defines the percentiles. But I'm going to show you another way to define the percentiles here. So our interquartile range would be 20 to 40 pounds. So it would be about an interquartile range of 20 pounds. I'm going to take a look at that Excel file that we started with as our last thing, just to show you that there's a lot of ways to skin a cat in statistics. I'm going to open up that Excel file again. Oh, yes. Okay, and I'm going to look at weight gain during pregnancy is this column here. Okay, this is 0. There's no value in there. Okay, I'm just going to leave it blank. Okay, and I'm going to take a look at the percentiles here. And the way I can take a look at the percentiles, I'll leave null in there. See if it'll actually work with this and not force me to blank those out. There's a lot of missing values there. I'm going to scroll all the way down here so I got somewhere to work. And there is a function in Excel called percentile. I lost track of it now. Which one is it? Weight gain during pregnancy. Which column was that? It is weight gain during pregnancy. This column H. Okay, column H. So we put equals percentile, right? Parentheses. And it asked me for an array and a value k. The array is going to be the list of numbers. And for us, that list of numbers is H2 colon H801. I know that because I remember how many values that were here. And I remember the first row, H1, was the label for the value. So I'm going to put a comma in there, and the K represents the percentile I'm interested in. I'm going to put in 0.25. And close the parentheses and hit enter. And it tells us that the 25th percentile is 20 pounds. Notice these are round numbers. That's why it came out so round before. I'm going to use the same function, equals percentile, parentheses, again, H2 colon H801, comma, except this time for the percentile, I'm going to put in 0.75. What weight represents the 75th percentile? 75% of women are below that value of weight gained. Oops. What did I do there? 0.75. There's a blank in front of there. I did something funky. Okay, that should work now. 0.75. Ah, my goodness. Percentile H2 colon H0. 0.75. See if it works this time. Contains an error. Oh, I misspelled percentile. That might help. Good. There we go. I'm rushing because I want to. I don't want to keep you looking at this constantly for tonight, and have you have it run over, and it's messing me up. Percentile parentheses H2 colon H801. You probably guys are correcting me now, and I'm not looking over there, right? 0.75, 75th percentile, and it comes up 40, just as we found with S. Yeah, I know. And every one of you guys was correcting me as I was doing this because you could see the error that I couldn't see. And the interquartile range is the difference between the 75th and the 21st percentile, or in other words, 20. So a lot of ways to skin a cat. You can use Excel to do a lot of this stuff. Now, there are add-on packages for Excel that do relatively complex statistics. Now, unfortunately for the Mac, guys, you Mac users that are using Excel, many of those packages do not work with the Mac. You may be able to find some that do, but there are several. You got to be a little bit careful because some of these add on packages don't work with a Mac version of Excel because Microsoft, in their wisdom, when they updated Excel a few years ago, 4 or 5 years ago, the version that they updated did not support Visual Basic, one of the programming languages that Excel uses for these people to develop these add-on packages. So some of these add-on packages do not work with the Mac version. So if you see one of these add-on packages that you're interested in, keep in mind you should check to make sure it works with your version of Excel. But that's just an example. There's a few ways to do this thing. You can even do things graphically in Excel, but certainly not as easily and as comfortably as in SPSS. Hopefully, this has recorded well, and you guys will be able to go back over this, including every little error or misstep that I've made in the process. Unfortunately, unless I'm too lazy to go back and edit them out, so you're going to see them again.